In this video, we're going to discuss resonance and formal charges. These instances occur when we have more than one possible Lewis structure. First, resonance. At times, more than one Lewis structure is necessary to represent a compound. Resonance is a concept in which the actual structure of the molecule or the polyatomic ion is represented by an average or a composite, a combination of two or more Lewis structures, which we call resonance structures. And in reality, none of these resonance structures actually exist. And we're going to see in the examples that we're going to look at two examples, ozone and benzene. Most times you use resonance structures where you have a double bond or a triple bond that can be present in one or more locations within the two-dimensional representation of the molecule. You say, well, do I draw the double bonds on the left side or do I draw them on the right side? And when you have the same amount of and the same type of adjacent atoms. So we're going to look at two examples, ozone and benzene, where we use resonance structures to give a more of a complete picture. Let's look first at ozone. Ozone layer we know is important to our existence here on Earth. It's used to shield out the sun's harmful UV rays. Okay, so let's look at the molecular structure of ozone. Ozone is also used in some applications for disinfection and water purification, disinfection. It's a pretty expensive process. Because you need to generate the ozone from molecular oxygen. But let's just look at the structure of it for resonance structures. Okay, so it's comprised of three oxygen atoms. Which one's central? Doesn't matter, they're all the same. Oxygen's in group 6A of the periodic table, so we have 6 valence electrons that we need to account for in the bonding. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. The next step in drawing a Lewis structure is to make the single bonds. So if we make single bonds here, we do not follow the octet rule. 2, 4, 6, 7. 2, 4, 6, 8. 2, 4, 6, 7. We need to do some sharing here. Okay. Now remember, the electrons are not set in the location that they're drawn when they're drawn around the atom. So what if we made a double bond over here, okay? And this lone electron over here, let's pair this lone electron there, okay? So now we have 2, 4, 6, 8 electrons around that oxygen, 2, 4, 6, 8 electrons around the central oxygen, and 2, 4, 6, 8 electrons around that oxygen. Okay. So if you're looking at that, you said, well, you know, I had a different idea. I was going to draw it like this. Guess what? You're right. Because in reality, we can't say that the double bond is on the left-hand side. And in reality, we can't say that the double bond is on the right-hand side because this molecule is three-dimensional, okay? We can rotate it, okay? So the double bond isn't necessarily on the left side or the right side, because if you're standing in front of it, it looks on the left side. If you're standing behind it, it would look like it's on the other side. So we have resonance structures here to show that either representation could be acceptable. So we use this double arrow here to show that either structure would be acceptable. What we do know is that we have one double bond and one single bond. Where the location of the single and double bond are, we can't pinpoint that. Okay, the molecule is not stuck on the board or stuck on a page. Okay, it's a three-dimensional molecule that we cannot see with our human eyes, but that exists. Let's do a second example, benzene. Benzene is a very important molecule in organic chemistry. It forms the backbone of many different large molecules in medicines, in particular steroids. You have benzene rings fused together, fibers, solvents. The benzene category, they're often called the aromatics because they usually have some kind of odor, usually a pleasant odor, but then again, that's a matter of opinion, pleasant or not. You have some kind of distinct odor, so they're called aromatics when you have this benzene ring as part of the structure. Benzene's made of 6 carbons and 6 hydrogens. The carbons are bonded together in a cycle. Okay. And then on each carbon, you have 1 hydrogen. Now, carbon has 4 valence electrons, okay? 1, 2, 3, I'm missing the 4th. So what happens is that you have alternating double and single bonds. Now, if we look, carbon will have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, but in reality, who's to say that those double bonds are located in the spots where I've drawn them at? We don't know that. We're going to see in the next chapter that those electrons are not what we say localized, okay, just like they weren't localized here. They're delocalized. So we need another resonance structure to show that the double bonds can be located between the other carbons where the single bonds are represented. So the resonance structure for benzene okay, draw all the hydrogens. The double bonds could be here. Okay. Okay, the double bonds are not localized, they are between alternating carbons. Now, you sometimes see a benzene molecule with the resonance structure shown a little bit different than this, and maybe when you learned in Chem 110, the very end, some organic chemistry, maybe not, but I'm going to show you because when you go to take organic chemistry, which I know a fair amount of you will, not all of you need to take it, but I know that a fair amount of you will, that we sometimes see this. That's the benzene ring. The points represent the carbons. Okay. 1 carbon, 2 carbons, 3, 4, 5, 6. Hydrogen's understood to be bonded to it unless you have some other symbol written. Circle represents that the double bonds are alternating or are delocalized. So that's also a resonance structure. That's more of a composite structure showing that you have the alternating double and single bonds and that those double bonds are not localized to a certain location. So we have resonance structures as one way to represent Lewis structures or a combination of Lewis structures that are correct. Then we have the concept of formal charges. And formal charges also help us to choose the better Lewis structure for representation of a molecule. And we're going to see how we calculate formal charges when we have more than one possible Lewis structure that we could write up with, okay? So if we could write the atoms in different locations, not necessarily as much the bonds. Let's see a couple examples of calculating formal charge and define what formal charge is. Formal charges are calculated to determine which Lewis structure is more stable. Therefore, which one is more stable is correct. The most stable one is the one which has the smallest formal charges, and any negative formal charge that resides on the most electronegative atoms. So we have a little formula here to calculate formal charge on each individual atom. The number of valence electrons on that atom minus the number of non-bonding electrons on that atom minus half the number of the bonding electrons on that atom. So we will look at an example, thiocyanate ion, where we can have multiple possibilities in theory for the Lewis structure of the thiocyanate ion. Now, if you remember, when I gave you rules for drawing Lewis structures, I kind of gave you a little built-in tip where I said when you need to determine the central atom, that if you have more than one atom that appears once in the formula, that you choose carbon. Let's see if the formal charges back up that statement. Let's see if the structure with carbon as the central atom is the most stable, or if one of the other structures with sulfur or nitrogen as the central atom is more stable. Let's look at the thiocyanate ion. Okay. 3 possible Lewis structures, okay, in theory. Now, if we have carbon as the central atom and the sulfur and the nitrogen as adjacent atoms, this would be the corresponding Lewis structure. Carbon, sulfur, and nitrogen have 8 electrons around them in this proposed Lewis structure. But let's say that we wanted to try nitrogen as the central atom, and we have this proposed Lewis structure. And then let's say in the third possibility, we have sulfur as the central atom with this Lewis structure. Every atom is following the octet rule in all 3 Lewis structure possibilities. So we don't have any issues there with the octet rule. But let's look at which one of these 3 would be the most stable. Okay, now I told you in the rules for drawing Lewis structures that carbon should be the central atom when it appears once in the formula, along with other atoms that appear once in the formula. So this one should be the one that results as the most stable. Let's see if the formal charge calculations back that up. We're going to look at each atom and calculate the formal charge of each atom. This is a bookkeeping technique that your book uses, which is actually good because you can get a lot of side calculations and lose your progress in calculating formal charges if you just scribble all over the page. This keeps it nice and neat, setting up this kind of format here. Let's look at each number of valence electrons. Sulfur's is in group 6A of the periodic table, so we have 6 valence electrons. Carbon's in group 4A of the periodic table, 4 valence electrons. Nitrogen is in group 5A of the periodic table, 5 valence electrons. Let's write those respective valence electrons under each atom and the other 2 proposed Lewis structures. Okay. Now, let's count the number of non-bonding electrons on each atom within the proposed Lewis structures for the thiocyanate ion. Non-bonding electrons on sulfur in this structure, we have 4, because we have 2 lone pairs. Okay, so 4 non-bonding electrons in this structure. If we look at carbon, there are no lone pairs, there are no non-bonding electrons, 0. Okay, remember, non-bonding electrons, lone pairs. A pair is 2 electrons. We have none. If we go to nitrogen, we have 4 non-bonding electrons equivalent to 2 lone pairs, 4 individual electrons. Let's look over at the second, structure B. Okay, we have 4 non-bonding electrons on this carbon, 0 on the nitrogen, and 4 on this sulfur. Okay, so non-bonding electrons, lone pairs, okay, but we want the individual number of electrons, not the number of pairs of non-bonding pairs. We want the actual electrons. And the same thing in structure C. Okay, nitrogen has 4 non-bonding electrons, sulfur has 0, and carbon has 4. Okay, now we need to take the number of bonding electrons and divide that in half. If we look at sulfur, sulfur has 2 bonds. 2 bonds equals 4 electrons. 4 divided by 2 is 2. Okay, if we look at carbon, carbon has 4 bonds, 4 times 2, 8 electrons. So we have that. We have 4 bonding electrons with this carbon. Nitrogen, we have a total of 4 electrons, 2 pairs, 2 bonding electrons. And those numbers reiterate over here as well because of the bond orders and the lone pairs. Okay, we have 2 bonding electrons, 4 bonding electrons divided by 2 to give us 2. Nitrogen has 8 bonding electrons divided by 2 for 4. Sulfur 2. Okay, and the pattern repeats over here, same way. Now let's calculate the formal charges. Remember, the formal charges are equal to the valence electrons minus non-bonding electrons minus 1/2 the number of bonding electrons. So we take this number and then subtract these 2. 6 minus 4 minus 2 is 0. Okay? 4 minus 0 is 4, minus 4 is 0. 5 minus 4 is 1. 1 minus 2 is -1. Okay, so I'm just subtracting this number minus minus. Okay, simple subtraction. 4 minus 4 is 0. 0 minus 2 is -2. 5 minus 0 is 5. Minus 4 is 1. 6 minus 4 is 2. 2 minus 2 is 0. Okay, so remember the formula that I'm using. Formal charge is equal to valence electrons minus non-bonding electrons minus 1/2 bonding electrons. Okay, I'm not pulling these numbers out of the air. I'm using this formula. I'm doing the math in my head because it's simple subtraction. 5 minus 4 is 1. 1 minus 2 is -1. 6 minus 0 is 6. Minus 4 is 2. 4 minus 4 is 0. 0 minus 2 is -2. Now we need to compare which structure would be the most stable and therefore the most correct. We're looking at this line right here. Which structure has the most zeros for formal charges? A. It has a negative charge. Does that reside on the most electronegative element? Well, if we look back, electronegativity values from section 9.6, nitrogen, even if you don't know the exact number for the charges, you know that electronegativity increases as you go across the periodic table. Nitrogen is the most electronegative out of sulfur, carbon, and nitrogen. That is the atom that has the negative charge on it. We have here -2, 1, 0, -1, 2, -2. Right here we have these positive numbers. Okay, we don't want that. That's not stable. Structure A is correct. Lowest formal charges. We have one last thing to address in Chapter 9. And I was kind of alluding to that term when I was talking about formal charges. I was talking about the bonds. Okay, I was talking about the bonds here. Okay. I dropped the term bond order, which I'll discuss a little more in Chapter 10. But we know that we have, with Lewis structures, we have possibilities of single bonds, double bonds, and triple bonds. And how those bonds relate in terms of the energy that they hold and the lengths that they are vary. Okay, last but not least, in Chapter 9, we have bond energies and bond lengths. Remember, the whole focus of Chapter 9 and then going into Chapter 10 is talking about bonding and structures. And, you know, ultimately, we have those tools to help us predict how molecules will react, how they behave for molecules that already exist and molecules that are to be discovered and synthesized. So we have three types of bonds that we can have between atoms. We can have single bonds, double bonds, and triple bonds. The energy of a triple bond is very strong. And we're going to revisit this concept again in Chapter 10 when we start to talk about shapes of molecules. And I have model kits I'm going to show you to illustrate this idea as well. So we have the strongest bonds are the triple bonds. And they're also the shortest. So they're very rigid, very little room for movement. You can't rotate them. They just kind of stay in place and maybe just move a little bit, okay? Double bonds are strong and they are a little bit longer than triple bonds, but the weakest bonds are the longest bonds. The single bonds are the weakest. They're easiest to break, and they are also the longest in terms of bond length. Tables 9.3 and 9.4 of your textbook give you actual values for comparison. The energies are listed in values of kilojoules per mole. And the bond lengths are typically reported in units of picometers, but sometimes you may see the unit of angstroms used. Okay, 1 meter is equal to 10 to the 12th picometers. 1 meter is equal to 10 to the 10th angstroms. These are units that are commonly used to represent the distances between atoms in a bond. Okay, so your single bonds are the weakest when it comes to energy, but they're the longest when it comes to bond length. And your triple bonds are the strongest. They have the most energy contained in them. So if you break a triple bond, you are releasing much more energy than if you break a single bond. The triple bonds are also the shortest in length. This concludes the video lectures for Chapter 9. Going into Chapter 10, we will continue our discussion of bonding And remember, what are the bonds made of? The bonds are made of electrons. So you see how chapters 8, 9, and 10 kind of follow along with each other to explain these concepts of bonding. Sometimes it can get a little bit theoretical, but and work a different part of our brain, but we need that part of our brain to be working to understand these concepts, and so that's what we're developing in this course. Okay, next lecture will be chapter 10.